Alright, here is our wheelchair lift. It is a prototype at this stage, a fairly good prototype now. It was our senior design project. At the time of our senior design presentation, it worked, but was very lacking in several respects. After the class was over, it kind of got put away for a bit, but started thinking about it, and it was troubling me that it wasn't working the way it should have been for as much money as we spent on it. We got funded for this project, and it felt like we needed to make a prototype that actually worked and actually did the desired movement. During the day of the presentation, I only did half the cycle. Now it is capable of doing the entire loading and unloading cycle. I'll go through that in more detail. So basically, let's get familiar with the components here. What we have is a 4-bar linkage here that is controlled by that stepper motor there in the back. It turns a lead screw, which is connected to a nut, and that moves this link back here. So this is our input link, and we have a gas spring here assisting the mechanism. We did SolidWorks simulations to position that correctly. So this stepper motor here and this stepper motor here are working off the same, not the same signal, but the same frequency, because they can't work off the same signal because of the calibration that needs to occur. The stepper motor in the back, that one moves this, I don't know, this collection of parts, which will house the, or not house, but is where we will attach the wheelchair to. That attachment point has not been constructed yet, but this is just to prove that the motion is there, and if someone desired to do so, they could attach a wheelchair to it and get it inside their vehicle. And we have a stepper motor up there, the third stepper motor that actually runs this lead screw here. Our initial design was not even close to this. We wanted the entire mechanism to take up a lot less space. Using some kinematic analysis, we designed a 4-bar linkage to put the wheelchair through 3 points of motion, but that linkage could not fit inside my Explorer, unfortunately. So we had to go with something like this. So these 3 stepper motors have to work together in order to get the mechanism outside the vehicle so the user can attach the wheelchair, and that's what these guys do. I designed these boards. The 3 bottom ones are stepper motor drivers that I designed in KiCad, and we etched those boards ourselves and assembled the components on them. If you want to know what the schematics are for those, I can attach them to this video. And this top board is actually the motherboard. The brains of these boards are the MSP430 microcontroller, the launch pad. It's made by Texas Instruments, and it's a nice little part. Anyway, each H-bridge driver has one of these microcontrollers on the board. They're running at 16 megahertz, and they are listening to the motherboard. And the motherboard sends signals to the 3 motor drivers in a coordinated manner. It tries to do this, without any glitches in there. So at the day of the presentation, we had these guys running at 1 megahertz, and everything worked kind of okay. There was a few glitches, and it turns out that some of the calculations involved in moving this mechanism were actually taking longer than 1 step to the stepper motor. So what was happening is a calculation would occur, and the microcontroller would have to do this calculation, but it took longer to do the calculation than to step one of the stepper motors. So it seemed like the program was hanging, and it really was. It was hanging on a calculation. Actually, I think it was a round function and some division and multiplication in there. So I sped these guys up to 8 megahertz, and it seemed to smooth that out a heck of a lot. The only problem is when I did that, the serial communication between the two of them got changed a little bit. So I started debugging the serial communication, and it seemed like the serial communication was buggy, and it was. And on the day of the presentation, we got lucky that it actually worked, because the latency involved in the program actually allowed the serial communication to occur like it should, but it wasn't actually doing it correctly, which was kind of funny. So I had to figure out what the heck was going on there and fix that in the software. And it turns out I wasn't even close. Well, I was close, but there was some tiny changes that had to occur in order to get the serial communication working correctly. And we'll take a look at the serial communication on the oscilloscope here in a second. So what we have, so it's all fine and dandy that we can control the mechanism, but we need to have the user have some input. And in order to do that, there's 4 buttons back here. These are the manual controls that the person could push these buttons and it'll move the mechanism. Those are sort of for debugging, and we actually I don't even use those anymore. But let's see. And then, so we wanted to be able to do it on board, and we also wanted to be able to do it remotely, and we did that with this wireless transmitter. I purchased this and purchased this board, but everything else we assembled ourselves. So this radio, at the point, there's only 2 functions, up and down, and calibration, I guess, but only 2 buttons actually do anything. The other 2 I haven't wrote any program for, and that's fine. They could be used for something else that completely hasn't even been thought of yet. So there's room for programming improvement for sure. Anyway, so okay, so when you boot up this thing for the first time, say we connect it to the car battery. This is around a 12-volt power supply. Say we connect it to the car battery. This mechanism has no idea what the heck's going on. It just got brought to life, basically, and it doesn't know where it is. So the first thing it should do when the user wants it to do something is check where the heck it's at. And it does that through the serial communication between these 2 chips. What's going on here is this chip here is monitoring a whole bunch of, well, so the reason there's 2 chips on here in the first place is because we didn't have enough pins on the microcontroller that I was familiar with to get everything hooked up. So we had to use 2 chips, and these 2 chips are talking to each other through the whole cycle, and they're very closely tied together. So this microcontroller here, I'm going to turn this off real quick so I don't shock anything or something like that. So this microcontroller here is listening to this pin out here. This goes through a DB9 connector, and it goes to some limit switches. So as you can see, here's a limit switch and a limit switch right there. So at this current moment, the wheelchair lift is in the loaded position and is connected, or is touching off right there. There's also one up here on the top. I don't know if you're there. There's a limit switch right there, and then there's a limit switches over here too. And that's why we need these 2 stepper motors to be going on the same frequency, but they need to have separate step signals, because during the calibration phase, what we're doing is touching off, and if this one touches off, it needs to stop that motor, but maybe that one needs to keep going, so until it touches off too, and then everything is square and lined. So it's listening through here for the switches, it's listening through here for the user input, and it's also listening through here for the user input. And then what happens is once the user pushes one of these buttons, what it does is this chip needs to figure out where the heck the mechanism is, and so it sends a information byte. Here, I'll show you real quick. I will attempt to load the mechanism, but since it's already loaded, it won't do anything. Come on. Oh, that's why. Let me set up the, let's do a single. Okay. Okay, there we go. Okay, so what happens is when the user pushes the button, is we got this going on inside the system. Okay. So what we're gonna have here is when the user pushes the button, this is going to be the main processor, and this is going to be the switch monitor. So they're the limit controls. So this guy is in, everything's kind of just sleeping until something happens. So as soon as a person pushes A or B or A or C on this, what it does is it triggers this, which is 1 byte of information. So this byte is associated between these two controllers as kind of an address byte. So it says, hey, I want this piece of information. It turns out this byte means I want to know where the limit switches are. Okay, so first thing that happens here is, so this guy sends it, and so this guy sends that first thing. This guy listens to that, and that's what this delay is right here. And then actually its delay is not only it's listening and also checking where the switches are. And then it sends this guy here, which is kind of an address byte that both of them also are familiar with, and it says, hey, the next piece of information is where the limit switches are. And the reason we have to have this is because what if the buttons are touched but someone didn't push a button? As in, what if we're loading the wheelchair mechanism and it's becoming inside the cycle? The main processor needs to know what is coming next every time in case it isn't actually directly asking for it. So in this case it's asking for it, but this is always there in case it isn't aware of what's going on. And so what will happen is the switch monitor will always tell it whenever these switches change position, no matter what. And what happens here is, what we have is at the time of this occurring, we only had 2. So here is the lead-in information, and then here's the actual information on the switches. And at the time of when I pushed this button, it turned out there was only 2 switches that were on, and so it probably moved a little bit. But here's the first, the start bit, and then the first one is on, and then the second one's off, and the third one's on, and then usually there's one right there, but it did not show up. But then what happens is, well, what if, so that information is good and all, but what if this main processor is doing something, or something terrible happens and it doesn't actually read it correctly? What it does is it echoes it back, exactly what it heard. It echoes it back, but if there was a transmission error, it'll echo back something incorrectly. And then if that were the case, this would repeat. It would repeat doing this until the information was correct. And then it would just kind of coast until something else occurred. So that's kind of the error checking within the serial communication. And we need to have that in case it sends it and it replies back incorrectly and then it just doesn't do anything. Well, that would mean that it's going to do something that this guy doesn't intend to do. So it's reacting to stuff that isn't true in the real world, and that would be bad, causing the mechanism to break or something like that. So that's the serial communication between just these 2 chips. So then if that information is correct, and if the main processor thinks that it can actually do something, I mean, it makes sense to move it out of the vehicle. Like at the time, it didn't make sense to move it into the vehicle because it was already at this position, but it would allow it to fall out of the vehicle. And then it would turn on these 3 H-bridge, double H-bridge stepper motor drivers, and then start sending them signals to turn. So let's do that. Show the full cycle. So we'll turn it on. Okay. Now let's see if this guy will work. It's kind of loud, but it would help if these stepper motor drivers had micro stepping, which I did not know how to do at the time. Turns out I kind of understand it now, but all that software was written by me, so sucks if I didn't know how to do it, right? So they're loud because they're doing just full steps, 200 steps per revolution, and they're only running at 12 volts, so the inductance inside the motors is a lot to overcome for this little 12 volt power supply in order to get them up to peak torque, and we need that peak torque in order to move this mechanism because it is kind of misaligned, and these bearings down here should not have been there, but they were. Anyway, let's try and load it into the vehicle first. Nothing should happen. Well, it did, because it wasn't fully calibrated. As you can see here, it wasn't calibrated completely. And now we'll run it again, and it looks like it's calibrated. We have all 3 limit switches connected, so that's good. Now it is capable of unloading out of the vehicle, but not loading. So let's see here. We'll try and load it in the vehicle. Nothing. Okay. Let's unload it. And we'll wait for the next one to hit when it hits bottom. Oh shit. Why did it do that? I think I need to take these off. Well, let's see what happened here. I'll try and recalibrate it. So we're gonna go to the top now. Okay, now we're at the top. I'm not sure what just happened. We'll try it again. Never seen that before. Well, I am unaware of what that could mean. I'm going to take these off, see if that has something to do with that. Try and recalibrate it to the top. Okay. I think those were causing the problem. I don't know why that would be. That's weird. So it's unloading the vehicle, or unloading out of the vehicle right now. What the heck? Well, I'm going to figure this out and continue.